we are going to be talking about heat capacity and calorimetry. And you are going to do a lab on this on Monday. And then on Tuesday, you'll have your quiz on this section. So we talked the other day about Q representing heat. And Q is going to represent our heat again here, that we're going to be transferring that heat from one thing to the next. We need to know the mass of the object that we're looking at. We need to know something called specific heat capacity. And then our change in temperature. So remember, delta means change in. So you're going to be subtracting those values to get your change in temperature. Now, this specific heat capacity is defined as the amount of energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius. So these are the units for that. Something with a high specific heat capacity is going to take a long time to heat up and a long time to cool down compared to things with low specific heat capacities. So for example, if you put a pot on the stove and turn the stove on and full blast and walked away for 5 minutes, well, let's do 3 minutes, okay? How would that pot feel when you, at the end of that 3 minutes, that metal pot? Would you want to touch it with your bare hand? No. You put a whole bunch of water, fill that pot up almost to the top with water, and you walk away and come back 3 minutes later. Can you still comfortably put your hand in that water? Yes. So it takes water much longer to heat up than metal. That makes sense? You've experienced that in your lifetime, probably, with the hot metals versus water. Water just takes, watch pot never boils because it takes so darn long to boil, right? Okay. So that's the idea behind here. Water has a very high specific heat capacity. All right. You need to be familiar with some terms here. You don't really need to worry too much about these calories, but there may be a couple problems on your homework with these. Knowing joules here, that is, or specific heat values, this equals 1 calorie, and then 1,000 calories equals 1 calorie. Notice the difference in the calories here. This one's a capital C, this one's a lowercase c. The other way that they would distinguish these is, instead of calling this a calorie, they might call it a kilocalorie with a small case c here. All right. And then we talked about what these different things mean. In some places, you might see an S here for specific heat capacity, but in AP and in here, we use a C. All right. So this is what a calorimeter looks like. This is kind of a crude calorimeter. They have fancier ones out there, but this is what we use here at school, and it actually is kind of effective, remarkably. It's just 2 cheap styrofoam Dollar Tree kind of cups. And then I've got some styrofoam that I've cut circles out of, and we fit that down in there. And we actually get some pretty decent results out of this lab. It's kind of surprising sometimes. All right. So what calorimetry does is you are going to be exchanging heat from a metal that you've heated into the water. And we can measure the temperature of the water with just a temperature probe. So it's not too difficult to make that happen. And whatever heat is lost by the metal is going to be gained by the water. Okay. So we can actually set these up where you have the mass of the metal times the specific heat of the metal times the change in temperature of that equals a negative, because the water is going to be gaining this, the mass of the water times the specific heat of the water times the delta T of the water. So we're going to end up doing lab next week where you're determining that. Here's some examples of lead and aluminum put in the same amount of water, but because aluminum specific heat is less than lead's, the or is higher, we're going to end up with a smaller amount of heat that's transferred versus the lead. So heating a system results in the system having greater energy because energy is flowing into that system. Cooling is going to have less. We've talked about these heating curves, and then if we flip this around on its axis, we would have the reverse. We could have a cooling curve. Specific heat then is measured as the amount of energy needed to raise 1 mole of a substance by 1 degree Celsius. You can also have molar heat capacity, which we're not going to really mess with much in here, but it's good to know about. You may have a couple homework problems on it. It is the amount of energy needed to raise 1 mole of a substance by 1 degree Celsius. So all they're doing is changing grams and moles around. Chemical systems then are going to change their energy through 3 processes. You can have heating and cooling, phase changes, and then chemical reactions. We can use this equation to calculate the heat when the temperature changes occur, and there is a change in that kinetic energy. And this is 6.5. We have 15.5 in here. We're in 15.5, which you're going to start on Tuesday. We are going to talk about heat changes when we go through phase changes. Because remember, this guy here that we've been talking about has a delta T. But if we're going through a phase change, what do we know about the temperature? Temperature during a phase change. What happens to the temperature during a phase change? It stays the same. That's why this line is like this, okay? So the temperature during a phase change is going to stay the same. So we can't use this delta T as a component of that because that would factor in as, if we multiply that out, you'd end up with what for your answer? Anything multiplied by 0? 0. So you'd end up with a 0 for your answer here. So we can't use this calculation, this equation for that. We've got to deal with that. And that's what we're going to look at on Tuesday to be able to make that happen. Okay. So we've got almonds and cashews here. This is what's called a bomb calorimeter. This is what they would use like in a place where they had like an actual good budget for stuff. And this is what they do to figure out how many calories there are in your food. They actually go through and they burn these things in this bomb calorimeter. So they'll ignite it with these ignition wires. They burn that sample in there, and then whatever heat is given off to the water is measured. And from there, they can see how much heat was given off by that material burning. So almonds and cashews were burned. The following data was collected. Calculate the energy for each nut and determine which provides more energy per gram. So we know that the mass of our water in our calorimeter was 2,000 milliliters. We have our specific heat of water here. We have our initial amount of grams of water, and we have our initial or our final temperature of water. So our water went up in temperature to 40.5. So we are going to take and we are going to figure out how much energy was produced in this reaction. So we had 2,000 milliliters. This says mass, but they gave us milliliters. How does that work? How can we get that to mass? What formula can we use? Go back to the very beginning of the year. One of the first formulas I gave you. I know you were in love with it. Right, density equals mass over volume. Remember, you were in love with it, mass over volume? Yeah. I know. It gets really corny when we get to that trivia day, the day before school ends. Like, yeah. You want it corny? Just wait. It's going to get worse. It's a fun day. It's not science trivia, you guys. You guys did a trivia before, right?
Yeah. No.
Where we were in at the end of the year.
We should do Jeopardy.
So we're doing end of the year trivia. So we do it with the other classes, and I'm working on the questions right now and stuff. So, but it was fun, right? I mean, it's not just sciencey kind of geeky stuff. It's kind of fun stuff. So you'll enjoy that day if you, assuming you come. Yep. Okay, so anyway, getting back to this, we need mass. So remember, the density of water is 1. So if we know that we have 2,000 milliliters, then how many grams would we have? Density is 1. This is 2,000. So what does my number have to be? Anything divided by itself is 1, right? So my grams have to be 2,000. Yes? Okay. So I'm just going to change this to a G. And then we can use it down in our problem here. So this is for my almonds. So 2,000 grams of water. We're going to multiply it by its specific heat, which is 4.18. And then we need to figure out the change in temperature. So my delta T is going to equal 22.5, 40.5, so 18. So that equals 18. Okay. So for my almond, times 4.18, I'm going to end up with 150,480. All right, see if you can do the same thing for the cashew. So QC is going to equal what? How'd you do? You get the right answer? I got that answer by taking the 1,000 grams of water. I multiplied it by the specific heat for water. And then I multiplied that by the change in temperature. So this was my change in temperature for this guy. So that is 28.8. So that's how I came up with that value.
Wait, so what does C represent?
C is your specific heat. This is your M, and then the difference between these two is going to be your delta T. Now they wanted to talk about mass of the nut here, so calories, which gave more energy per gram. So we're going to take the energy of our almond. So this is going to be our almond. And we're going to do 15,048.0. We're going to divide it by its mass, which was 6 grams. And they didn't specify units for our value, so we're okay there. So I'm going to take that divided by 6. I'm going to get 25080 joules per gram. For my cashew, oh, I love cashews, you guys. They're so good. I'm going to take the 120384. I'm going to divide it by the 5 grams. And that's going to end up giving us 5,016 joules per gram. So calculate the energy, which one gives more per gram. That would be our almond. That was not a good circle. Let's try that again. So the almond is going to give us more per gram compared to the Did I? I don't think I did that right.
No?
No, I did.
That would be like 25,000.
Yeah, I got 24,000, like 76.
So what did I do wrong there? Did I drop a 0 or something? Oh, I grabbed the wrong number. That's what I did. Divided by 5. There we go. Okay, how's this? I'm still going to be right by circling it, but my value's very much off. Better?
I got 0.8, but yeah, pretty much.
Yeah, it's 0.8. I was being lazy. Okay, better? Sorry. Bad. Good calling me out, guys. That's a good thing. All right, let's look at the last one here that we're going to do together today. We've got 50 mils of HCl. We're adding that to NaOH. The initial temperature was 19.8. The final temperature was 26.3. They want to calculate the heat gained by the mixture. I think in this one we have to assume that these are mostly water, so the specific heat of them is still going to be that 4.18. Heat gained. So heat gained, final mixture temperature. Okay, so we are going to take, our mass is going to be 50 and 50. So our mass is going to be 100 because this is mostly water. We're just going to consider this water. We're going to consider these grams, okay? So that means that we've got 100 grams times the 4.18, which is the specific heat for water, times our delta T, which it went from this value up to this value. So 19.8 and 26.3. So it's 6.5 is my delta T. So we're going to calculate our Q value. 100 times 4.18. So I got my Q value equaling, and check my math because I've already made a mistake today. That's going to be joules. All right. Then, what is the heat of reaction per mole of NaOH? So, heat of reaction per mole. So that would be 2717. We can figure out our moles because we can multiply 0.05 times 0.5, which is 0.025. So remember the molarity and the milliliters. molarity equals moles over liters. So if we're solving for this guy and we know the molarity is 0.5 and we know that this guy in liters is 0.05, I can multiply those together and that's going to give me my mole amount. So that's how I ended up with the 0.025. Let's see if I can calculate correctly here. Okay, that is a big number. So that is 108680, and that would be joules per mole. There you go. I think we have 3 more note packs left for the year.
Oh, I'm sorry. I have a question. Where do we get the 0.025?
That's from right here. You take the molarity of the NaOH, and you've got your volume in liters here. I multiply those together. That's going to give me moles, which is this value.
Oh.
All right. So you've got homework this weekend on this.